Welcome to this lecture series in group theory. Last time we looked at the notion of direct products. I don't want to recall it because we don't need it for this lecture and it's a very simple notion anyway. So these are the problems. And now let us see some more examples of groups. So today we'll be looking at three different examples. The first is the Klein-4 group. So this is the Klein, I think it's a subscript. Oops. Klein. So what is this group? This is a set of 4 elements, and this is the table which is depicting the binary operation. So E star E is E, E star A is A, E star B is B, and so on. A star E is A, and A star A is E, A star B is C, A star C is B, and so on. So this is how the binary operation is given. So this is a very nice way to actually, if you have a small group, then you can just draw a table for the binary operation. It's a very nice way to express the binary operation. And one can check easily that this is a group. For instance, E acts as the identity, and one can check associativity and inverse. So A is its own inverse, for instance. A star A is E, and B star B is E, so B is its own inverse. C star C is E, so C is its own inverse. So this is a very abstract way of writing down a group, but this Klein-4 group can be realized in a very concrete way, which is the symmetries of a rectangle. So take a rectangle, not a square, but a rectangle. So these two sides are different. Okay, basically we are considering those orthogonal transformations which preserve all the vertices, meaning each vertex gets mapped to a vertex. So only those orthogonal transformations. This is exactly what we did for dihedral groups, where we considered regular polygons. Here we are taking a rectangle. A rectangle is not a regular polygon, but basically you could say that we are taking the quote-unquote dihedral group of the rectangle. So if this, this reflection about this horizontal line, which takes this vertex to that, and that vertex to that, and this vertex to that, and this vertex to that, this, if you denote that by A, and similarly the reflection about this line by B, and the 180-degree rotation by C, then you'll see that actually all these things, the composition of A and B is actually given by this table. So the composition of A and B is C, and you can try that either visually or by hand. That if you apply A, then this vertex goes here, and then you apply B, this vertex goes here, which is same as saying that this rectangle, at least as far as this vertex is concerned, this rectangle is rotated by 180 degree. But the same is happening with every other vertex. This vertex, once you apply A, comes here, and then you again apply A, then you apply B, it comes here. So this vertex is also sort of getting rotated 180 degree, and you can just see that with every other vertex. So this operation, first you apply A, then you apply B, A times B. This is same as C, the operation C. So all of these operations actually match with the picture here, and the Klein-4 group is thus the group of symmetries of a rectangle in the plane. Okay, now we look at the Quaternion group. This is a much more complicated group. It has 8 elements, which we denote this way, and this is the multiplication table, or the whatever binary operation, the table depicting the binary operation. And I mean, these have to do with rotations in 3 dimensions, but I don't want to get into that. And another way of expressing the same group is this, where instead of bars we put a minus. So, and instead of E we are writing a 1. And with these relations, basically, instead of writing the whole table, if you just record these relations, you will be able to compute everything in this group. Anyway, so of course it takes a little bit of an effort to check that this is indeed a group, but you can believe it, or if you want, you can check it. Okay, finally I want to discuss the groups coming from taking roots of unity. So fix some positive integer n, and then consider the group G, or rather the set G, defined in this way. So take all the nth roots of unity, all the complex numbers which when you raise to the power n gives you 1. So this is a group under complex multiplication, meaning just the usual multiplication of complex numbers, and I leave you to check this as an exercise that this is indeed a group. And for the sake of a better understanding, one can depict this via picture. So for n equals 3, you will see 3 different roots. Basically, they will be, this is 120 degree or pi by 3. I think 2 pi by 3. 2 pi by 3 radians. Okay. So these 3 points on the unit circle. So yeah, one thing you can note is that every element of G is lying on the unit circle, because if z to the n equals 1, then mod z to the n is also equal to 1, which implies that the length, or what should I say, the distance from the origin of z is 1. So all of these things lie on the unit circle, and for n equals 3, you get 3 points, and this is how they look. Okay, there is not much else that I want to say in this lecture. Basically, these are some more examples of the groups, and we should keep these in mind as we go along. The more examples we know, the better we understand. And with this, I end this lecture. So as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.